When the average person thinks of particle physics, they imagine city-sized particle accelerators and chalkboards filled with equations. This is also the typical fantasy of a naive physics student, as I once was. But in reality, as a particle physics researcher, I spend most of my time writing code. So with that today, I'm going to be convincing you that in order to be a physicist of any field, you need to also be a computer scientist. In practically any modern physics experiment, there will be a lot of data involved, more in fact than any of us could probably imagine. Let's take a look at some examples. I picked 3 random modern physics papers to illustrate this point. From this first paper on gravitational waves, we have plots with too many data points to even see. From this other one on the subatomic tau particle, we have plots with the number of particle collisions plotted on the y-axis being on the order of 10 to the 5, or 100,000 particle collisions per x-axis bin. Then lastly, we have one on modern superconductors with a number of different high-resolution plots which require a lot of data themselves from the experiment. Point is, every single modern physics experiment results in a lot of data. While 100 plus years ago, this wasn't necessarily the case. In theory, they could build an experiment, perform it, and make conclusions on the spot. We've seen this in the Michelson-Morley experiment to prove that there was no ether, the double slit experiment to demonstrate light interference, the Foucault pendulum to prove Earth's rotation. I could keep going for a while, and all of these experiments only required something like 0.01 megabytes of data. Now, comparing that to some of the most famous modern physics experiments, we can visualize how high this number has come. Starting from 0.01 megabytes for a single run of the Michelson-Morley experiment, we have reached over 10 to the 9 megabytes of data for a single experimental run of particle collisions to show just a signature of the Higgs boson. Now, knowing that modern physics experiments have a lot of data, and also knowing that humans trying to understand this raw data would probably not go so well, what is there to do? We need some way to make sense of this data. And we can do so with something you might have heard of. It's called a computer. We can take all of that complex data and turn it into a nice, colorful plot for us humans to understand. And this is where computer science comes in, which is essentially the study of how to instruct a computer to do what you want it to do. And unfortunately, although it would be nice, we don't have a herd of computer scientists to just do it for us, so we have to do it ourselves. Unless, of course, we were to become powerful professors and we could just tell our undergrads or graduate students to do it for us. But until then, we have to do it ourselves. With that in mind, let me tell you what it really means to be a physicist. Being a physicist means knowing how to plot any set of data using buggy programming libraries like Root that you would hope could only exist in your nightmares. It also means knowing how to run complex simulations taking into account every single relevant physical law and the subtle processes involved to test a given hypothesis or match against real data. A physicist also needs to know how to implement and sometimes even partially design machine learning models to learn higher level information from a given dataset. Designing algorithms, creating specialized data structures, implementing parallel computing, staying organized by storing your code on Git. I mean, these are all things you would think that a software engineer or computer scientist would do, not necessarily a physicist. Not only that, but us undergrad and graduate physics researchers have to present our findings that all this computer science shenanigans led us to our group leader, only to think it over and nonchalantly tell us to make these insanely time-consuming changes that would take us hours. But that's enough complaining. In reality, I would argue that this isn't even a bad thing. Unless you absolutely hate coding, unarguably hate it, then this really is a very good thing. Coding, designing algorithms, simulating, these are all very difficult things to do, but they also require a lot of critical thinking, very deep logic. Thus, computer science is an incredible means of strengthening one's intelligence. Of course, it's necessary in the process of determining meaningful things in physics, but it's also a great tool to help make oneself a smarter person. My particle physics research is mostly coding, like I said, but I can't even tell you how much my critical thinking skills have improved. My mind is completely different in the best way possible. And with that, I'd like to conclude the video with this. Today, every single university incorporates mandatory computer and coding courses into its physics major's curriculum, and for very good reason, as we just saw. However, do yourself a favor. If you're thinking of getting into physics, make sure that coding isn't a deal breaker, because you will probably not enjoy what you're doing if it is. And if it isn't a deal breaker, get ready to become smarter than you could even imagine. So with that, thank you for watching. Leave a like and subscribe if you enjoyed, and I'll see you in the next one.